Hi everyone, welcome to lecture 6. That is the headline result of this mini-series. It is the Möbius inversion formula. Now so far, we have built all the pieces, divisor of sum, and arithmetic function, the Möbius function mu, and Dirichlet convolution and special function like 1 and epsilon. Now, and of course, in the previous lecture, we covered the fundamental identity that is convolution of mu with 1 that equal to epsilon, right? The identity. Now, in this lecture, we put it all together. So the main result here is that if we have a function g from the divisor sum of some function fd, we can actually get back f from g through the mu. We can treat the mu as the inverse filter for the divisor sum. That's the key result. We're going to go over the proof, and then later on, we're going to work on the torsion function phi and square free indicator in later on lectures. Whenever you see a divisor sum, now Möbius inversion could help. Let's get into the lecture.
Last time we proved that the convolution of mu with the constant 1 function gives the identity epsilon. That result told us that mu is the function that cancels out plane averaging over divisors.
So today we are starting from a function g that is built as a divisor sum of some hidden function f, and we want to recover f from g for every n, right?
Exactly. The equation defining g on this slide, where g of n is the sum of f of d over the divisors of n, is the central puzzle. Möbius inversion will give us a clean algebraic way to solve that puzzle for any such pair f and g. To feel how information gets blurred, look at the example for n equal to 6. The value g of 6 is the sum of several values of f, one for each divisor. If you only know the total g of 6, you cannot immediately tell what each individual f value was.
So divisor sums are like mixing together several ingredients into one number. If we can somehow subtract off the right pieces, we might be able to isolate the original f values.
That is the picture. Möbius inversion will supply the precise recipe for undoing this mixing. You can think of mu as a carefully tuned filter that, when convolved with g, reconstructs f from all these overlapping divisor sums. To make the story precise, we work with arithmetic functions from the positive integers to the complex numbers, and we combine them using Dirichlet convolution. The formula on the slide says that the convolution of f and g at n is a sum over the divisors d of n of f of d times g of n divided by d.
So g, in our earlier example, was really the convolution of f with the constant 1 function, because we multiplied by 1 and added over divisors.
Exactly. Alongside that constant 1 function, there is the identity epsilon, which is 1 only at n equal to 1 and 0 elsewhere. And there is mu, the Möbius function that changes sign depending on the prime factorization and vanishes on numbers with repeated prime factors. These three functions interact beautifully under convolution. Now we can state the Möbius inversion theorem. Suppose g is obtained from f by convolving with the constant 1 function, which means g of n is the sum of the values f of d over all divisors d of n. The theorem says that you can recover f by convolving g with mu.
On the slide I see two explicit formulas for f of n. One uses g of n divided by d, the other uses g of d. Are those really saying the same thing?
They are. Because convolution is commutative, it does not matter whether you view the divisor variable as d or as n divided by d. One formula groups the weight mu with the divisor d, and the other groups it with the complementary factor n over d, but they both compute the same recovered value f of n. Let us prove the theorem using only the algebra of convolution. We start from the assumption that g equals f convolved with the constant 1 function. Then we convolve both sides with mu, so we get g convolved with mu on the left, and on the right we have f convolved with 1 and then with mu.
Where do associativity and the identity epsilon come in here?
Associativity lets us regroup the right-hand side as f convolved with the convolution of 1 and mu. But from the previous lecture, we know that 1 convolved with mu is epsilon, the identity for convolution. Convolving any function with epsilon gives the function back, so we conclude that g convolved with mu equals f. That is exactly the inversion formula. Here is a classic application. There is a well-known identity that for each n, the number n equals the sum of phi of d over all divisors d of n. In other words, the identity function that sends n to n is the convolution of phi with the constant 1 function.
So in this language, the identity function is playing the role of g, and phi is playing the role of f in the Möbius inversion theorem.
Right. Since the identity function equals phi convolved with 1, the inversion theorem tells us that phi equals the identity convolved with mu. The formula at the bottom expresses phi of n as n times a weighted average over its divisors, with the weights coming from mu divided by d. Let us compute phi of 12 using the new formula. The equation on the slide writes phi of 12 as a sum over the divisors of 12 of mu of each divisor times 12 divided by that divisor. Then we plug in the values of mu at each divisor and simplify.
That is why you listed the divisors and the values of mu for each one in the bullets. We multiply each mu value by the corresponding 12 over d, and then add them all up.
Exactly. When you carry out that arithmetic, you get 12 minus 6 minus 4 plus 0 plus 2 plus 0, which simplifies to 4. That matches the fact that there are exactly 4 numbers between 1 and 12 that are coprime to 12. To see the power of the inversion principle, look at the constant 1 function. Suppose 1 is equal to some function f convolved with the constant 1 function. If we apply Möbius inversion, the equations on the slide show that f must equal 1 convolved with mu, which in turn is epsilon.
Then if f is epsilon, convolving epsilon with the constant 1 function must give back the constant 1 function, right? That sounds like a good consistency check.
Yes. When you convolve epsilon with the constant 1 function, only the term with divisor equal to 1 survives, so the result is always 1. Rewriting that convolution as an explicit divisor sum recovers the familiar identity that the sum of mu over the divisors of n equals epsilon of n. Let us step back and summarize. The Möbius function is the inverse, under Dirichlet convolution, of the constant 1 function. Because of that, it allows us to undo any divisor sum that comes from convolving with 1.
So whenever I see a function g that is a sum of values of some unknown f over divisors, I can write g as f convolved with 1, and then I know f is g convolved with mu.
Exactly. That principle leads to the 2 equivalent divisor sum formulas for f of n that we have used today. They are powerful tools for turning global information about a function, expressed as sums over divisors, into local information at each n, and they show up throughout number theory and multiplicative functions. To practice, look at the equation on this slide where g of n equals n, given as a sum of unknown values f of d over the divisors of n. Treat g as the identity function and apply Möbius inversion to solve for f.
If g is the identity function, then by analogy with the phi example, f should be the identity convolved with mu. So f of n should be n times a sum of mu of d divided by d over the divisors d of n.
That is right. More concretely, the solution is that f of n equals the sum over divisors d of n of mu of d times n divided by d. Finally, take a moment to reflect. In all of these examples, mu acts like a sharpening filter that cancels out the overcounting in divisor sums and restores the original function f.
Thank you for your time in watching this. Please like, share, and subscribe to the channel. Of course, we always would like to hear from you. Please make your comments below.